Hi student, welcome to my channel Education Shop. In this video, we'll solve example 3.9 that is from heat transfer by Cengel. Example 3.9 is relevant about heat loss from an insulated electric wire. Insulation is provided over this electric wire. This insulation is made of plastic. Let's come toward its statement. 3 millimeter diameters. The diameters of the pipe this is the diameters of the pipe. And its diameter is given, that is 3 millimeter, and 5 meter long electric wire. The length of the wire is 5 meter. Is tightly wrapped with a 2 millimeter thick plastic cover whose thermal conductivity is 0.15 watt per meter Kelvin. This wire is wrapped in a millimeter thick plastic cover whose thermal conductivity is also given, that is 0.15 watt per meter Kelvin. Let's say the thickness of this plastic cover that is provided over this electric wire is x, and it is given 2 mm. Electrical measurement indicate that a current of 10 ampere passes through the wire. And also by electrical measurement we have noticed that an electric current is passing through this wire 10 ampere, and there is a voltage drop of 8 volt along the wire. On the electric wire, the voltage on this electric wire, the voltage drop is 8 volt. If the insulated wire is exposed to a medium of 3 centigrade, and this electric wire that is insulated by plastic cover is exposed in a medium, outside temperature is 30 centigrade, that is given, and the heat transfer coefficient of this medium is also given, that is, let's say H, here it is given, and it is 12 watt per meter square Kelvin. What we need to determine the temperatures at the interface of the wire, mean to say this temperature T1, that is our concern to find, this is our requirement. Determine the temperatures at the interface of the wire and the plastic cover in a steady operation. Also determine whether doubling the thickness of the plastic cover will increase or decrease the interface temperature. In the next step, it is asking about thickness of this plastic cover is increased to 2x, then tell us whether the temperatures T1 will increase or decrease. That is all. Let me write the data that is provided in the statement. A 3 millimeter diameter of this wire is given, is, let's say D1, that is 3 millimeter, and the radius of this wire is R1, and it is equal to D1 divided by 2. It is 3 divided by 2. We will get its value, that is 1.5 millimeter. Convert that into meter, just simply 1.5 millimeter. To convert that into meter, just simply divide this 1.5 by 1000, and you will get its value, that is 0.0015 meter. The length of the wire is also given, that is 5 meter, and the thickness of the plastic that is provided over the wire, that is 2 millimeter. Let's say X is the thickness of the plastic, is 2 millimeter, or you can say that 2 divided by 1000, you will get 0.002 meter. And the thermal conductivity of this plastic cover that is provided over the wire is 0.15 watt per meter Kelvin. The current that is flowing in the wire is 10 ampere. The voltage that is provided across this wire is 8 volt. The outside temperature is 30 centigrade, and the outside heat transfer coefficient is H, and it is 12 watt per meter square Kelvin. We need to find the temperature is T1, and in the second case, what it says, if the thickness of the cover is increases times, whether this T1 will increase or this T1 value decrease. That is our concern to find in the second requirement. Now let's come toward its solution. We need to calculate the amount of heat that is generated in this wire. It is equal to Q dot equal to the current that is passing in this wire and the voltage applied on it. Current is 10 ampere and the voltage is 80 watt. Heat is generated in this electric wire, and this 80 watt heat that is generated in this electric wire. Next we need to find this R2 value. If you look at this diagram, this R2 value is nothing but it is equal to the sum of this R1 plus the thickness of this plastic cover that is provided over this wire. That's why I can say that R2 is equal to R1 plus X, the thickness of the plastic cover. This R1 value 1.5 millimeter plus X value, that is 2 millimeter. Simply add and you will get its value, that is 3.5 millimeter. To convert that into meter, divide by 1000 and you will get 0.0035 meter. The next thing that is required is to find the surface area of this insulated wire. This represents the whole surface area of this insulated wire, and it is equal to A2 2 pi R2 L. 2 pi is constant, R2 value is 0.0035, L is the thickness of the pipe, that is 5 meter, Simply multiply and you will get A2 value, and it is 0.11 meter square. This is the whole surface area of this insulated pipe I have showed on this cross-section line. Let me draw the thermal network diagram. The heat that is generated in this electric wire by passing current through it. The temperatures at the surface of the wire is T1, let's say. When the heat is transferred from T1 to T2, this plastic cover offers some resistance to the heat transfer. This is, let's say, RP. Resistance offered to the heat transfer by this plastic cover, and then heat is transferred through the surrounding medium, and the mode of heat transfer is convection heat transfer. And similarly, the resistance offered by convection heat transfer is, let's say, R convection, and then temperature drops to the outside temperature T infinity, that is 130 centigrade. Now let's find this RP value. RP is the resistance offered the heat transfer by this plastic cover, that is equal to ln outer radius, this is the R divided by R1, and divided by 2 pi KL. A is the thermal conductivity of the plastic cover. Now just simply enters the value. The natural log ln. R2 value is 3.5 millimeter. This is the R1 value, that is 1.5 millimeter. 2 pi conductivity of the plastic cover, that is 0.15, and length of the wire is 5. Let me solve this on calculators and you will get the RP value. Press this equal button and you will get the RP value, that is 0.18 almost centigrade per watt. Next is to find the RC value, resistance offered by convection heat transfer, that is 1 divided by surface area of the insulated pipe A2, and H, that is 0.11 meter square, and H value is 12, and you solve this on calculators, you will get its value almost 0.76 centigrade per watt. Our total resistance is RT, that is the sum of RP plus RC simply added, that is 0.18 plus 0.76. When you add it, you will get the total resistance, that is 0.94 centigrade per watt. Next, we know that heat transfer rate is equal to change in temperature divided by the total resistance, and it is equal to T1 minus outside temperatures T infinity divided by total resistance R. And we already calculated the heat that is used inside this electric wire is 80 watt. The temperature T1 is our concern to find, and the outside temperature is 30 centigrade, where the RT value, that is 0.9. Divide both sides on 0.94. We'll cancel out with this. Can say that T1 is equal to 0.94 multiply 80 plus 30. When you solve this on calculator, you will get the T1 value, that is 105 centigrade. Before answering the second part of this statement, you need to calculate the critical radius for this electric wire. Critical radius is RCR, that is denoted by RCR, that is equal to HA divided by H. H is the thermal conductivity of the plastic cover, that is 0.15, and convection heat transfer in which it is exposed to the medium, that is 12. It will give you the critical radius of insulation, that is 0.0125 almost, or to convert into millimeter, multiply 1000 value and you will get 12.5 millimeter. In the statement it says if the plastic thickness increases 2 times, let's say 2x, then the dimension of the outer radius R2 becomes equal to R1 plus 2x, and R1 value is 1.5 millimeter plus 2 into x value is 2 millimeter, and the outer radius will give you the values of this become 1.5, this become 4, means equal to 4.5 millimeter. If you compare these two values, the R2 value is less than critical radius of insulation. Then it shows that by doubling the plastic cover thickness, it will increase the heat transfer. If heat transfer is increases, the value of T1 will also increase. If I draw the graph of critical radius and heat transfer, it will clearly understand you. On the x-axis, this is the value of radius, this is the critical radius value, this, let's say in our this case, that is 12.5 millimeter, and here is the heat transfer rate. As your value is reaching towards the critical radius, the heat transfer is increases. Let's say our value is 4.5 millimeter. If you are increasing plastic cover thickness up to critical radius, the heat transfer will obviously increase. But if you increase beyond 12.5 millimeters, then the heat transfer will drop. Here you can see this. I hope you understand. If still there is confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Thank you so much.